So the genesis of this talk, the reason why it came about was, so StackPath introduced an edge compute platform, just over a year or so ago. And the marketing folks came out to me and said, hey, you're the performance guy. How much faster is edge over cloud? In other words, why do we care? Give us a number. And I kept saying things like, well, it depends. There's a lot of variables that go into it. And they didn't feel this was a very good answer. And frankly, they were right. So what I did was I went through some of the older literature to say, well, when you're studying speedups, how much faster is execution time for one approach versus another approach?
Nathan, sorry,
And,
sorry,
yes,
I'm just going to interrupt a second. We've got your presenter view rather than the slides.
Oh, that's terrible. We can't have that. Oh, now I have to fix it. It's terrible. All right, let me see if I can just display this instead, and we'll just sort of go from here. I hope this isn't too bad.
Just fine.
The genesis of the talk was, we need to know how much faster is edge than cloud. It winds up being a very difficult project. It's a very complex problem to solve. It's very, very difficult to come up with an easy answer. There is no simple answer. So instead, the approach was to go back and find a simplified model which can do a better job of trying to explain the sort of speed differences that we would actually expect to guess. And the goal behind this is to be able to come up with something which is a usable approach to deliver an actual real-world result, such that we can go back and say, well, you should use edge over cloud for certain use cases, you should not use it for others, and most importantly, why? And answering the question why is the goal of this talk. So it all starts with a gentleman by the name of Gene Amdahl. So Gene Amdahl he unfortunately passed away just a few years ago. But he's very, very famous because he was one of the pioneers in the computing field. He was one of the very, very first people to ever build a computer. It was, in fact, his PhD thesis when he was a student at the University of Wisconsin-Madison. So he built one of the very first computers there. And based largely on the strength of his solution, IBM wound up hiring him as the chief architect on the System 360 project. So this is, again, we're talking very, very early days of the computing world. This is the dawn of the mainframes. If you're familiar with System 360, another gentleman who worked on the project went by the name of Fred Brooks. Fred Brooks wrote a very famous book called The Mythical Man Month, which hopefully is still famous in this day and age. So he worked very closely with Gene. And Gene Amdahl went on to found the Amdahl Corporation, and he had his own very long and storied history. But what do we care about here? What we're looking at here is a paper he wrote from 1967 called The Validity of the Single Processor Approach to Achieving Large-Scale Computing Capabilities. What he was really arguing about is the fact that in the very, very early, even from the very early days of the computing world, there was this big question of how do you make a task faster? Is it better to keep working on faster and faster CPUs, or is it better to throw more CPUs at the problem? So he went through this, developed this model, he went through it, the conclusions of the model, and what he came up with is a very concrete criticism. This is worthwhile bringing up in large part because I want everyone to think in terms of the way the modern internet works. We have this huge number of computers which are all linked together. We have this massive number of clients and servers scattered literally throughout the globe, and we have these massive networks that were built up to allow everything to interlink and to be able to talk to each other. And we came up with all these ways of solving problems in a very, very diverse and spread out manner. What does Gene Amdahl say about this? He critiqued this. He said this was absolutely positively the wrong way to do it, that the world should not have gone in this direction. Why? And again, think of the modern world. When he says things like, for over a decade, prophets have voiced the contention that the organization of a single computer has reached its limits, and that truly significant advances can be made only by interconnection of a multiplicity of computers in such a manner as to permit cooperative solution. In other words, our linked modern world was the wrong approach. We did the wrong thing. We didn't build it the way that he felt that it should. Demonstration is made of the continued validity of the single processor approach and of the weaknesses of the multiple processor approach in terms of application to real problems and their attendant irregularities. So when we have these big multi-processor solutions, there's a lot of weaknesses and issues associated with this that we have chosen to do regardless. So we built the modern world regardless of the problems that Gene Amdahl identified. Which is why he's saying things like a fairly obvious conclusion which can be drawn at this point is that the effort expended on achieving high parallel processing rates is wasted unless it is accompanied by achievements in sequential processing rates of very nearly the same magnitude. So why did we build the modern world the way that we built it? And more importantly, why is that a bad thing? So in the paper, he comes up with this formulation. And strictly speaking, if you read the paper, technically, although it's well described in the paper, this particular formulation was derived slightly after, but that's just historical footnote. So there are three key things we have to worry about in this model. One is the speed up that we can get out of the code. So if we parallelize something, we run it across multiple CPUs, what kind of speed up can we expect? That's this big capital S. And it says that, well, that speed up is dependent upon two factors. One of which is we have part of the task which is amenable to some sort of speed up, meaning throw an extra CPU at it. By how much does that part speed up when we add an extra CPU? And that's our little s value. And the second thing that we care about is P. What was the proportion of execution time that the part benefiting from improved resources originally occupied, which is to say that this is a percentage between 0 and 100%. It's a proportion. So if we can accelerate the whole thing, that's a proportion of 100%. If we can accelerate none of it, that's a proportion of 0%. And so we see the proportion is bounded. It has to be between 0 and 1. So three things. What happens if our proportion pushes off towards 0? What happens if a proportion pushes off towards 1? Right, this is just the percentage of the execution task which actually can be improved, because not usually not the entire thing can be. So what is he saying? He's saying that if the proportion is 0, if there is not a single part of this task that we can improve its speed on, then the ratio, the amount of speed up we could get, the capital S, is bounded at 1, right? Because that means if there's no speed up, the time taken after is equal to the time taken before a factor of 1. And that's why that factor of 1 is important. But if we get a perfect linear speed up, so given some speed up S, little s, that means the maximum speed up of the entire task, as opposed to just a proportion of the task, is going to be equal to that original value little s. So it means it's going to increase perfectly linearly. So if s is 1, we get perfect linear speed up, which looks like this. So it defines our solution space. We now have boundaries on our solution space. We say that our expected ratio of improvement can never be greater than the value that we have for little of s, that the proportion that we can actually improve, that bounds the maximum that we can actually improve the whole thing by. And so our solution has to exist within the triangle that's described between the orange line and the gray line. Great. So what does this mean for actual parallel programs? Why is this a big deal? Where do we get at the heart of the criticism? The problem is that because little s's are speed up of the part of the task, what if we made that infinite? What if we could take part of the task and speed that up by an infinite amount? So not a factor of 10, not a factor of 100, but literally an infinite amount. The formula says that if we improve little s by an infinite amount, the maximum speed up we can expect out of the total task is bounded. And it's bounded by the proportion of the task which is amenable to the speed up. 1 over 1 minus p. 1 minus p is the percentage of the task which is amenable to speed up. And it gets worse because if we take a look at this, there's a bound. Great. Can we plot out the bound? Yes. And when you plot out the bound, you notice it goes horizontal incredibly quickly. So it's not just bounded, it's bounded at relatively small values of s for small values of p. So if there's a proportion of the task that can be sped up is less than 90%, I think 90% is a big number, but if it's less than 90%, we hit the knee in the performance curve. We go horizontal. Our performance curves just hits its maximum very, very early on for even small values of s. So even as we're trying to throw more and more CPUs at the problem, if our percentage P is on the order of 90%, then it doesn't matter how many CPUs we have. We actually bound out at a very low number of CPUs. And this is why he had such a big complaint about this, and why he was saying that, well, this increased parallelization, this just is not a very good solution for 1967. So he's got some very, very different things to say about the modern world. And a simple compare and contrast shows that, sure, in 1967, if you had 10 CPUs in a server, this was a big deal. Very uncommon, very expensive. But yet, here we are in 2020, and all of a sudden, more than 100 CPUs in a server is normal, which means you can have more than 10,000 CPUs in a data center, and that's normal. And if you have multiple data centers, getting more than 100,000 CPUs is normal. And so guys actually have this. All the big hyperscalers can do this. Why? So the modern world, especially in terms of cloud computing, looks something like this. You have end users scattered all over the world. Since this is a US conference, I'm choosing the United States to show. Pick the four corners of the country, pick a provider with a cloud presence right in the middle of the country, say Council Bluffs, Iowa. And all of a sudden, you can see that everybody is able to talk. Everybody's network is set up, and we still are able to talk to a proper client-server architecture, and that everybody can communicate, everybody can execute tasks by submitting them to the central processor. The central processor does it and returns the result back to the end user. Why does this work? Because this was against what Amdahl was saying. It says this works because we intrinsically have a massive amount of parallelism in modern web applications. And how do we get this? Well, part of it is the global distribution. Yes, we have people from literally all over the world, and they're connected. So you're not just have a small number of computers here and there, but each end user has an individual atomic execution request. So you have an HTTP request, it goes up, it can get satisfied, can get returned, and they don't have a ton of dependencies. So one end user makes a request for, say, static content, some other user makes a request for the same static content. It doesn't matter. There's no dependency between those two requests, so they can be satisfied in parallel very, very easily. And as a result, we have the percentage of the problem, the proportion, the amount of the problem which is amenable to acceleration, to throwing another CPU at it, is huge. It's absolutely enormous. It's much, much bigger than 0. It still has to be less than 1, but it's big. And not only that, but the amount that we can accelerate it by is absolutely enormous in these 100-odd CPU beasts. We have the machines, we have the computers that can execute this stuff much, much faster than a single CPU server can do it. So once we've realized that, then the other question is, well, do we have other ways of pushing our values for S even higher, given that we have an incredibly high value for P? And the answer to that is pretty easy. Yes, of course we can. This is why Edge was built. And once we recognize that we have these incredibly high values of P and we could justify building cloud built, once you say that, well, we can improve the value of S even higher by building out multiple POPs. Why are we stuck with cloud? Let's move straight into Edge. All of a sudden, we can start seeing if you put a POP on top of every single population center, then you can be guaranteed that all your end users are talking to what is legitimately the lowest possible latency server, the guy that's literally next door to them. And that's sort of the idea behind Edge. Because now we can drive a bigger value from S, not just from the lower latency, but if you note, if I have, say, 20 POPs as opposed to one cloud, so 20 POPs in Edge versus one cloud, by the very nature of having 20 POPs, I'm going to have a lot more CPUs, just because I have to scatter them across 20 POPs as opposed to putting all my CPUs in a single POP. So intrinsically, I'm going to have more. And this also drives these bigger values of S, these bigger factors of improvement that I can push through. Now, like I said, Gene Amdahl did not see this as the future, and yet we built it anyway. Why? And it's because we are in a corner case of Amdahl's law. And that corner case is that the bigger the value of P is, and we have to get closer and closer and closer to 1, but at these super high values of P, even very small differences result in a very drastic speed up. And that's what this graph is trying to show, of comparing what if I have 99.9% versus 99.99% for my value of P. And you can just visually looking, all of a sudden, yes, there's still a bound. Yes, eventually the curve does go horizontal, but that occurs at a massively, massively higher scale than it did back at p equals 90%, or worse, p equals 50%. So we are in an edge case, we're in a corner case where this thing actually makes sense and we can get away with this. So having realized this, let's take advantage of the opportunity to try to put some numbers to this. We get the general framework, we see what the general model is trying to tell us, and we see why we think we have this silver lining. We think why it is that we're in a reasonable landing spot. We've actually found a part of that solution space that justifies this particular solution. So let's put some numbers to that. Now, I want to emphasize that this is illustrative. These are not exact numbers. These are not real-world benchmarks. This is deliberately chosen illustrative numbers, which are meant for easy mental math, and they're meant to describe the general, what the model is saying, much more it is than it's trying to perfectly replicate an exact real-world example. So what we're going to do is we're going to try to estimate the value of P for a large load-balanced multiprocessor system versus a small single-processor virtual machine, where the task is high-volume static object delivery over HTTP. Standard content delivery. And again, this is illustrative. This is not exact. Nobody in their right mind would use a single CPU server for this task. This is illustrative. So what do we know? We're going to assume that our load is 1 million end users exactly. Again, easy mental math. Everyone's going to make a single request for a 1 megabyte object, which gets delivered in 1 second. Obvious mental math. And each CPU can process exactly 1,000 requests per second. And our load times, well, how long does it take to satisfy this particular task? Well, we're going to have two systems, right? We're going to compare a large load balanced multiprocessor system versus a single CPU system. The single CPU system, we're going to say, takes 1,000 seconds to execute and satisfy all these million requests, whereas the large load balanced system takes 2 seconds. And under these assumptions, we can calculate what's the speed up of the multiprocessors of 1,000 CPUs versus 1. What's 1,000 CPUs versus 1? And in our model, we're claiming that gives us an actual observed speed up of a factor of 500. And that's just 1,000 seconds, which is the time it took for the 1 CPU machine to do it, divided by the 2 seconds it took for the multiprocessor to do it. That's a factor of 500. We assume that our speed up, our value for little s, of the part that was amenable to speed up, what was that speed up? That part speed up was a factor of 1,000 because we have 1,000 CPUs versus 1. That's a ratio of 1,000. And all we have to do is plug these two values into our equation to get the third one to pop out, which is the proportion. So what was the proportion? 0.9989. 0.9989 is very, very close to 1. We really are in that edge case. We really are in that corner case where we have such incredibly high parallelism that we can get away with just throwing CPUs at the problem and giving guaranteed a very reasonable speed up, that we're actually getting something back out of this. This is not a wasted exercise at all. So when you plot it out, it looks something like this. We are that lovely gray line right here. Yes, we're still below the maximum theoretical, according to the model, of s equals 1, excuse me, of p equals 1. And that would be that perfect linear scaling. So we're not getting perfect linear scaling, but we don't have to. We're still doing a lot better than we would be if our p-value were even 99%. So we're at 99.89. In other words, we can still get away with throwing a bunch of CPUs at the problem. So great. Once we've validated that we are in this window of opportunity, that we actually can get away with doing this, why do I care about edge versus cloud? We talked a little bit about latencies. We talked a little bit about number of servers, about CPU counts, about the nature of the population density of our end users to guarantee these super low latencies. Well, now that we have calculated a value for P, and we only cared about two things. We cared about S and little s and capital S. Well, little s, let's assume that our edge has 2,000 CPUs, our cloud has 1,000 CPUs. Well, that gives us a little s value. The speed up value now is a factor of 2. That's 2,000 CPUs divided by 1,000 CPUs. We already have our value of P that we calculated just a moment ago. And so our predicted speed up over moving from cloud to edge, now just plugging the numbers in, we're at a speed up of just under a factor of 2, 1.9978. In other words, our value of P was so high, we had such high intrinsic parallelization that moving to edge actually does result in a major speed up over cloud. So according to model, and when you go and measure it, now we still have a little bit of a problem because now we have assumed that we could derive our value of P experimentally, which is what we did in our little thought experiment here. We figured out that we could get a good value for little s, again, from the experiment, and that drove our calculable speed up, which lets us say that small systems benchmarking can apply to this particular model, which will derive what our actual projected speed up is going to be. And the moment we have that, we can actually go through and do a proper make or buy decision. Now we can calculate an actual cost to benefit ratio of moving from cloud to edge, because we know what the speed up is going to be without having done it in the first place. And this is the value of the model. This is why this was a big deal. This is why we had to keep saying things like, well, you know, it depends. Because the question isn't what's the values of P and S for our little thought experiment. The question is, what's the value of P and S for your application? And if you're willing to engage in the small systems benchmarking necessary to derive those values for your own application, and they will differ from application to application, which is why the answer to how much faster is edge than cloud is always, well, it depends, because it depends upon the specifics of your application, the level of parallelism within your application. That will drive the observed actual benefit that you're going to get in moving to edge. And that's kind of the punchline of the thing, is that the moment you have any two of those three parameters, the third is calculated. So the benefit here is its application. So you have the conceptual model. You can now start assigning dollar figures to the expected speed up. What's the difference in latency going to do to your revenue numbers? And based on that, you can now make an actual dollar and cents decision. Is this worthwhile for me to do? And is it worthwhile for my application to do? And I want to leave that off with this one little side conclusion, which maybe I didn't make obvious because I was talking so much about CPUs, but I really want to emphasize that resources is a generic term. So it doesn't have to be just throw more CPUs at the problem. It can also be, let me reduce my latencies between end user and servers. And that's also a speed up. Actually, if there's time, I have another example demonstrating of what that means. But it could also be, what if I improve my disk subsystem? What if I improve my I/O? What if I improve other aspects of my performance? The law gives you a way to estimate what the total performance benefit is going to be, or the total speed up that you are going to get through that particular improvement to your system. So this is actually a wonderfully generic very happy to open up the floor to any kind of questions, anything anybody wants to talk about. And of course, I will be in the chat as well as questions verbally right now.
Nathan, that was an excellent presentation. Thank you so much for that. And yeah, if there's any questions you guys have out on the floor, do pop them into the chat room, or you can lift your camera and click raise hand to bubble yourself up to the top in the participants list so that we can bring you into the video feed to have a chat with Nathan yourself. Nathan, I'm just going to stop your presentation so that we can see you properly. So you, right at the end there, you started talking about sort of some very key areas to have a look at, like disk I/O and things like that. In your experience, what are the, in practical terms, what are the most impacting things that people in the audience here could go back to their infrastructures and have a look at that that might give them the best performance increase? There must be some common scenarios that you've seen.
Oh, of course, that's an excellent question. I'm really latency, meaning the time between our, actually, if you don't mind, I actually have a slide on this, if you don't, on the latency, if you don't mind bringing that back up. Let me pull up one of the appendix slides. But because it talks about one of the effects of decreasing latencies. So one of the problems with network requests is that you spend a huge amount of time in communications time. And of course, the greater the latency, the greater the time you spend. And so we can go off on things like bandwidth delay product, which is a very, very good demonstration of this effect, right? The longer the latency gets, the lower your effective bandwidth becomes, because you're spending that much more time on communications overhead, just the length of time it takes to get a packet to acknowledge that that packet's come back. So anything you can do to decrease that latencies becomes a really, really big deal. And that is, in my opinion, probably the single most important factor here. I think that most people know enough to do the internal benchmarking to know that, well, if I improve my disk, I can get this. If I improve my local IO, I get that. But realistically, in a client-server architecture, that latency out to the client is just an absolute utter killer.
I've just had a question in on the chat room there, which is a very simple one, which is, will the presentation be available post-Zoom meeting? So I'll, assuming that's shareable, I'll grab that off you, Nathan, and make sure we get that shared out through the conference systems and so on. But John, if you need it, email me and I'll connect you with Nathan. So any other questions from the floor, chaps? I've got another one for Nathan if there's nothing forthcoming from you guys. I'll give you a second to type. They're not typing quickly enough. Maybe we've got questions about how fast they can type. Yeah, so in the context of say a live video streaming model, which is kind of the sort of given vertically integrated challenge that most of us face, would you instinctively look for technologies like multicast to deploy out to the edge to get your parallelization more efficiently deployed, or are there other sort of common technologies like that that you might recommend people investigate?
There are several. There absolutely are several, and it largely comes down to use case, unfortunately. So there's a tremendous amount of customization here for things like live broadcast. Absolutely, multicast is a very useful tool for that, because now all of a sudden you have this one-to-many connection, and so you can reduce the total amount of bandwidth that you really care about to the minimum. So in other words, you have a centralized location, you use multicast to push out to an edge. Those edges then can then multiplex out to a very, very large number of people. And so you get these scaling functions. So you get these lovely, lovely scaling functions at multiple steps along the way. I will say that for other things like on-demand content, you really don't have that luxury, and you're stuck. You still have to take advantage of edge in this scenario, but you have a reduced number of possible optimization steps. So you're looking at, do you move the processing to the data, or do you move the data to the processing? And when it comes to on-demand, you really have to start moving the data to the processing. So you're looking at either replication or some other techniques of zipping things up and unzipping on the fly. So you want to reduce the amount of information you have to have in flight at any given instant.
So you and I have often chatted about microservices, which we did at the when we last met in Streaming Media West and so on. And I know you're a great fan, so am I. I think microservices architectures are enabling new models where, as the parallelization and the scaling requirements change, you can actually move function around midstream or while processes are being active and so on. Again, up in the sort of application space, are there other techniques and methods that you think are applicable to improving the performance in this in these cases?
Oh, absolutely. And again, I apologize because I have to give the same answer I give the marketing folks. It depends upon your use case.
Yeah.
So some use cases are incredibly amenable to a ton of optimization techniques, and others aren't. Others are a lot more stubborn. And so you have to think very, very carefully through what your intended use case is going to be in order to line up the appropriate optimization for it. That said, yes, there's a ton of stuff that goes on right now. I'm glad you brought up microservices. Just continuing along with that, as you break your problem down, you realize very quickly that anything that can be done locally needs to get done locally. And this is one of those really wonderful benefits of microservices, especially in terms of a remotely asynchronous environment. So if you're going to break your problem out, you know you have a dependency, and reordering them, things have to come back in the appropriate order in order to deliver the final result that you actually want. And so you're stuck. Now you have to go back and make sure that you have appropriate bounds, you have appropriate bulkheads, that you know what your error modes are in order to make sure that you can still deliver a quality experience. But Yes, breaking things out via a microservice, you can split out the various aspects of, say, logging into one microservice. You can split other aspects of the serving pipeline into other parts, other different microservices. And so long as you have them all coming back within enough time, you have the appropriate bounds on the latency to actually deliver the result.
Perfect. And there's a question in, from John on the chat. So are there examples of good infrastructure partners, such as AWS or Microsoft Azure, that can support live delivery in these models?
Well, obviously, I do work for StackPath, so I am contractually obligated to bring up the word StackPath when that question comes up, although I promise that our solution is a good one. But yes, there absolutely are multiple good infrastructure partners. And I apologize for sounding like a broken record. The specifics come down to your use case, because every partner is better or worse at different aspects of the problem. And you need to make sure that what they do well lines up with what you need to do well. So.
Perfect. Well, Jonathan was happy with that answers. He's given me a got it, thanks. That's great. We were just chatting in the production chat we've got running here to sort of keep everything going, but we were just saying how nice it was to have some proper maths up on the Content Delivery Summit rather than conjecture about pricing models, which is just great. So science triumphs, hurrah!
Right. Victory.
So Nathan, I'd like to say a huge thank you for that presentation. It was great to have that in there, and we look forward to hopefully chatting more in the chat room, or if we open up the mics at the end of the day, chatting a little bit more if you're still around then. But thank you once again. It's been fantastic to have you.
Of course. Wonderful. Thank you for having me.